Hello, everyone. Welcome back. Today, we want to talk about solving exponential equations, what it means to solve an exponential equation, and then what an exponential equation is first, then how to solve it. So our goals then are to be able to identify first, in solving an exponential equation, you identify that's what it is, and then you obviously want to be able to solve it. So we'll take a look at both, and we'll look at a couple application problems. So number one, or first off, let's take a look at the left where it says solving exponential equations. Now, here's what an exponential equation is. It's an equation where the variable to be determined, what we're looking for, the x or whatever, is in the exponents. That's what makes it an exponential equation. Okay, so here's one example, and there are many kinds of examples of these you can see. This is what we're going to focus on today. I can actually use space there. So this is our example we'll be looking at. And it's so similar to this. Okay, so this is an exponential equation because our variable to be solved, or our variable we need to find, x, is in the exponent. And in this case, both exponential expressions have the same base. You have one exponential expression equal to another. They both have the same base. That's what we'll be focusing on today. There are other kinds of exponential equations, but this is what we're looking on for now. So we have a property we're going to use. It says this. Basically, you have down here below, if you have a to the u equals a to the v, then u equals v. So what that means is, remember, a solution is anything that makes an equation, makes a statement true. We want to find the x, will make the statement true. So if we compare both of these, then if we have the same, in both cases where these two exponential expressions equal to each other, if the bases are the same, then in order for them to be equal, the exponents have to be the same. That's what that says. I say that below. So in words, if the exponential expressions are equal and they have the same base, the exponents themselves must be equal. So it also says below, here's our strategy for solving. So let's take a look at our first example on the right. And our direction is just be to solve. Let's actually look at this one here. So number one is going to be just that. 2 to the 7th is equal to 2 to the x plus 3. Now, we have one exponential expression equal to each other, and the bases are equal. As we can see, they're both 2. So what that means then the exponents are equal. Okay, so then we equate the exponents to each other. We have 7 is equal to x plus 3. And this is easy to solve then. Just subtract 3 from both sides. We get that x is equal to 4. We plug 4 in, we can see that 4 plus 3 is 7. So you have 2 to the 7th on each side. So this is the solution. Right? So that's the concept. Let's look at one more example. So let me actually move. What you see below is an application problem we'll look at in just a moment. Let me actually move that to the next page. There we go. Then we'll come back and take a look at another example. So there are other kinds of exponential expressions, ones in which both sides are not written to an exponent, but this is what we're going to focus on today. So now let's take a look at number 2. Now let's say we have this. So let's say we have, how about 8 to the x squared plus 5x is equal to 8 to the 6th. Of course, also, if you multiply this out, you'd also would have this exponential expression equal to a number. But for here, we're going to focus on the ones where they're written like this. So this is like the first one in the sense that both our bases are equal. We have two exponential expressions equal to each other. Both the bases are the same. That means the exponents are equal. So this means that x squared plus, oops, I actually need to make this I should make this a negative 6. X squared plus 5x is equal to negative 6. There we go. And that's because of what the nature of the exponents. Okay, now recognize this is a quadratic equation because our highest power is x squared. And so the best way to, in most cases, approach solving those is set one side equal to 0. So I'm going to make the right side 0. So I'll then add 6 to both sides. And that's going to give me x squared plus 5x plus 6 is equal to 0. Now, this equation will factor. Not all quadratic equations are. but this will factor. And if we factor it, what we see is we're going to have x plus 2 times x plus 3. Then to solve this, write that 3 better. So to solve an equation like this in factored form, this side is equal to 0. We know if we multiply 0 times anything, we get 0. So if we find a number that will make either one of these 0, that will be a solution because 0 times anything is 0. So we say each one equal to 0 to find what will make each factor 0. And then we get x equals -2 and x equals -3. Those are our solutions. So if you plug either one of those into this equation, you'll get a true statement. Now, so that's the idea of solving these kinds of exponential equations. Now let's take a quick look at an application problem, actually a couple application problems. So this one is actually one taken out of a textbook. So it says light intensity I relative to the depth in feet, one of the clearest bodies of water in the world, the Sargasso Sea, can be approximated by this equation. Now let me actually enlarge this a bit so I can see this equation better. So I put it to, there we go. Hopefully I can get all the words in. Yes, I can get all the words in. You see this a bit better. So what this is a mathematical model of the light intensity in this Sargasso Sea. We're basically starting at where D is the depth. So of course D equals 0 is at the surface. Let's think about that. So this is I equals I0. We'll explain what I0 means in a minute. E to the negative 0.00942 times D. So if D is 0 at the surface, then E to the 0 is 0. I'm sorry, it was 1. E to the 0 is 1. So then I equals I0. So this I0 then is what's called it's the intensity of light at the surface where D is 0. Okay, that's the light intensity of light coming in. So what I want to see then is how much intensity of the light drops off the further we go. If you've ever been diving, or if you've seen pictures of divers or people diving deep underwater, you know that basically if you go far enough, then it becomes very dark because light is basically absorbed and scattered away. So that's what's happening is the intensity of the light falls off and tends to fall off in an exponential way as you go deeper in the water. So that's our mathematical model. And then the question is what percentage of the surface light will reach a depth of 50 feet? Okay. Now, so in this case, our depth is 50. But if you notice, we just plug D in itself, we would still have this I0. We don't know what that is. It doesn't tell us. But what it asks for is a percentage. Okay. Let's explain that. So find percentage. So make that look more like a D instead of a P. I'm going to find the percentage of the light basically a percentage of the light that's at the surface, which is I0. Okay, so I want to find the depth of 50 feet, what percentage of that light that started out as I0 at the surface we still have. So actually the way we can figure this out is actually if we take this equation and divide both sides by I0, let's see what that does. So if we do that, we have I over I0 is equal to, of course, I0 times e to the negative 0.00942 d. Okay, divide this by I0. Of course, over here, the I0s cancel out. What we have left then is just I0 is equal to just this exponential e to the negative 0.00942 d. Okay, well, sorry, I over I0, and this I over I0 is the fraction of I'll call it the original light based on the light at the surface that makes it to depth D. Okay, that's a T. So basically, this is a fraction of the original light, I0, that makes it the depth D. Let's think about that. Okay, so I0 is what you start with at the surface, and this is what you're left with. Remember, light is decreasing, so what you're left with is some depth D. Okay, so this is just a fraction of that. Okay, so then we just need to figure out this exponential. I was going to let me move this a little more space. So we need to find, we need to approximate this value, I equals I0, is equal to e to the negative 0.00942 times d, and our d is 50, when this is in feet. Okay, now we're actually going to calculate that. You can use a graphing calculator or calculator if you want. Actually, I'm going to use Desmos, which is can also be used as a calculator. So let's actually go to that really quickly. So actually, let me start back. So Desmos is a program some of you may be familiar with. So it's desmos.com. Type that in, just hit graphing calculator. Now, we can, of course, graph with it. You can also use it simply for calculating things. So let's put that in. So first I type E. Okay, it recognizes that is about 2.718. Then do the rooftop, which gives the exponential. Now I'm also going to use a parenthesis here to make sure I get everything as an exponential. So negative 0.00942, then times 50. And that gives me the answer. So 0.62, and I'm already said to round it to, but about 0.6243 is our result. So let's go back, 0.6243, let's go back and take a look. So it was approximately 0.6243. Okay, actually, to say what to round it to. Now this is a decimal, so the percent is this 0.6243 times 100, which is going to be then 62.43%. So what this says, at a depth of 50 feet, based on this equation, this mathematical model, about 62% of the light that started out the surface has made it to 50 feet. Okay. Now, let's take a look at one more example. This one we're actually going to use Excel to help us with this. So this example, it says this table below shows the life expectancy in years at birth for residents of the United States from 1970 to 2010. Let X represent the years since 1970. Find an exponential regression model for this data and use it to estimate life expectancy of a person born in 2025. Now, here's a table, and this is taken out of a textbook for this data. Now, a regression model essentially means that we're going to find like a best fit model. Okay, so let me actually set the regression. A regression model is a best fit. It's called a best fit model for data, or best fit equation for the data. So we choose what type of equation we want, either a straight line or an exponent or some other kind of graph, maybe a parabola. And then we use some computer program, which we use Excel here in a moment, then to find the one that fits that data best, starting with that kind of model. So what I've done is that let's go into Excel. I've already typed these values in. And one thing I've changed is the problem states we want to go back and look at this. It says, let X represent the year since 1970. Okay, so we're going to treat 1970 as 0 year. So let's go to Excel. So that's what I've done. I've just changed this. So this is 1970. Then 40 years after 1970 is 2010. Then I put in those same life expectancy values. It's the same table, except starting at 0 for 1970 and then going up to 2010. Now, the way to create a best fit model in Excel, so click on your first data set, and then while holding that button down, drag down for all your data. Go up here to insert, and you see various charts and things where it says charts. So click on that, right click on that, it's where it says scatter, do the first one. Okay, so this is our basic model. Now here it looks fairly close to a line, but we want to use an exponential model. So from here, and also this is also a later version of Excel, where the plus, click on this plus, you give several options. One of them is a trend line. That's where we're going to click on trend line. Now, we'll click on the arrow because the original trend line starts out as a straight line. So let's click on this. See some other options here. Even though it says exponential, I'm going to go to more options because it will give us more of what we need. So click on more options. So right now I'm on linear. I'm going to click on exponential. Then also just not only want that, but I also want my equation. So it's sort of standard where it says display equation chart. I also need that. Okay. So let's drag this down. Maybe we can enlarge it a bit. This is my equation. This is the equation of this exponential model. It goes through that. So if I write that down, it's going to be 71.631 times e to the 0.0023x. So if you can see that, of course, you can enlarge that if you like. Enlarge it a bit myself. Yeah, 0.0023x. Now, I'm going to go back here. Let's take a look. Let's write down. So the best fit exponential model is y equals 71.631 times e to the 0.0023x, where x is our, once again, our year since 1970. So the question we want to do is to estimate life expectancy of a person born in 2025. Okay, so for person born in 2025. Now we count the years from so once again, x equals 0 in 1970. So in 2025, that x would be equal to 55. Okay, so we're going to plug that in. And so we're going to have y is equal to 71.631 times e to the 0.0023 times 55. Now, I'm also going to use that on Desmos. So let's go back to that. It's also a good way to show you the calculation. So this time e raised, use the rooftop, also use parentheses. Now this time it's not negative since it's an increasing function. So 0.00, oops, I forgot my, hang on. I can fix that in a moment. So 0.0023 times 55. Now that's not the answer because I have a number out in front. I can always add that right here. So 71.631. And you see the exponential, so life expectancy is about, just about a little 81 years. So 81 years and maybe 2.5 months or something like that, 81.29 years. Now, also let me say something about that. Although we got a value, if you notice, the data we collected was stopped at 2010. And here we're trying to do life expectancy for someone born in 2025, which is outside our data range. that's potentially kind of in statistics, that can be a potentially, you have to be careful about doing that. Be a potentially dangerous thing to do in statistics, because we don't know for sure if our trend is changing anyway significantly past 2010, since that's where our data. This is, if I ask you what was the life expectancy for someone born in like a 2002, that would be within our data set, within our data range, year range. That's what's called interpolation. If you're going between your data, within your data range, if you go outside your data range, that's called extrapolation. And that can potentially be dangerous because there may be some different trends going on outside the data we have. So you have to be careful of that. But anyway, what that does, it suggests that a person born in 2025 using this mathematical model, this equation, this best fit exponential model, is about 81.29 years. So what we've seen so far today, how to solve basic exponential equations, and then also solve some application problems involving exponential expressions. Thank you. Have a good day.